talk about dark energy and accelerating universe. This is lecture 29. Uh, Dark energy is another cosmological constant, and then we're going to talk about the discovery of an accelerating universe. Uh, there's a problem with matter-dominant flat universe. We already know that the apparent contradiction between inflation prediction of flat universe, which is verified by observation, but CMB anisotropy, and the fact uh, the matter density is not equal to the critical density, omega is not equal to 1. So we have a problem with a matter dominating flat universe. First of all, here it's a missing energy problem because the Freeman equation relates the curvature to the density. And so if k equals 0, the universe must have exactly the critical density, omega naught is equal to 1. Yet we observe, including both the baryonic and dark matter, only about a third of this value. Okay, radiation energy actually is negligible, small, and so at present the matter densities, baryon and dark matter together is only about 0.31. So if the universe is flat, it appears that we will have a missing energy problem because we have k equals 0 yet does not have omega equal to 1. Actually, another problem in the lecture 23, we talked about the time evolution universe. For a matter-dominant flat universe, we should have an age equal to about two-thirds of a Hubble time. And the Hubble time is about 14.5 billion years. So therefore, two-thirds is about, we're talking about 10 billion years for a flat universe, which is shorter than the estimated age of old stars, notable the globular cluster, which we deduced has age older than 10 billion years, 12 billion years. So it appears that we have a cosmic age problem for matter-dominant flat universe. A possible resolution of these phenomenological difficulties of a flat universe, hence inflation cosmology, would be to assume the presence of dark energy. Okay, so what is a dark energy? Recall the definition of the equation state parameter W, which is the pressure divided by the energy density. Dark energy is defined as an energy component having a negative pressure corresponding to this equation state parameter W less than one-third. Okay, so in the dark energy dominant universe, according to the second Freeman equation, the second derivative of scale factor A double dot which is proportion minus pressure plus a third of energy density. So therefore, if the pressure is equal to W rho c squared, so factor rho c squared, I have this minus W plus one-third. So therefore, the definite W less than minus one-third, if this less than minus one-third, then this parenthesis is negative because the minus in front of it. So therefore, a double dot will be positive. Okay, so therefore we're going to have accelerated expansion correspond to a gravitational repulsion because remember negative pressure goes to gravitational repulsion. So right, the dark energy is defined of something that has the equation state parameter less than one-third. First of all, I'll give a warning. The name dark energy is some sense it's not accurate and not descriptive because we tend to confuse, some people confuse dark energy with energy of neutrinos or black holes because these are clearly non-luminous, so therefore dark, so they have energy, but they are not counted as dark energy. They're counted part of dark matter because associated pressure is not negative for black holes and neutrinos. So in fact, they associate with gravitational attraction rather than repulsion. So, so make sure don't confuse that. The simplest example of dark energy is Einstein's cosmological constant. Remember, Al's constant is pressure equal to minus the pressure density, so therefore the W would be minus 1. Minus 1, of course, less than minus one third. This cosmological constant, of course, also does not have the immense size as the one that drove the inflation. Okay, because we're talking also cosmological already, but that's for inflation. That's a huge value. But here it's not maybe because what we need the cosmological constant here is to solve the missing energy problem of flat universe. So therefore, the dark energy density should be should be just provide the missing 2/3 of the critical density, because the matter plus dark energy together should be 1. Also, an unvanished cosmological constant would also provide a repulsion to accelerate the expansion of the universe. In such an accelerated universe, the expansion rate, by definition, is in the past must be smaller because A dot is getting bigger and bigger. So then the current rate. This means it would have taken a longer period of time because the acceleration was smaller to reach the present universe than the flat matter-dominant universe. So therefore, this way we expected the age universe to be greater than 2/3 of Hubble time. So therefore, dark energy might might solve the cosmic age problem. Okay. So dark energy can potentially solve both the missing energy and the cosmic age problem. So let's look at the Hubble curve. I remember Hubble diagram is a plot of the distance, in fact, luminous distance from the source, uh, and I guess it's measure redshift. Okay, so the Hubble curve is a function of luminosity distance as a function of the redshift. Because light from distant galaxies reach us by moving with finite speed, so it took a while for them to reach here. So the measured light from the star further out in distance is to probe the cosmos further back in time. Okay. So therefore, you're talking about further away the distance, which we're talking about further back in time. So therefore, here is now, and all out here is in the past. Okay, the more away it is, the more back in time also. An accelerating expansion means that the expansion rate, okay, was smaller in the past, which you said. So which means the Hubble constant must be smaller in the past, right? Because Hubble constant is A dot, or A dot over A. In the Hubble diagram, which plots luminosity distance against the observed redshift, the Hubble curve of an accelerated universe bends upward. These dotted lines are supposed to represent part of the Hubble curve. So it claims that in the accelerated universe, this curve will bend upward. Okay. Namely, the object given for a given redshift z must be located further away than otherwise from the decelerating or empty universe. Here's the Hubble relation. Remember, the the redshift is proportional to distance, and the proportion constant is related to the Hubble constant. Now, so for a fixed z, and if the h is smaller in the past, Hubble constant is smaller in the past. So if this is smaller, in order to have this fixed z, d must be bigger. Okay, so therefore, it must be further away. Okay, so this is what we're talking about. So that's why the Hubble curve must bend upwards. Okay. So it's further than expected. It was the accelerated universe, the observed light source will be dimmer than expected compared with in a decelerating or empty universe. Okay. So that's the thing you're looking for. Somehow you find the light appears to be dimmer than you would expect it. So we're going to talk about supernova 1A as a standard candle. In order to observe the changing expansion rate of the universe, that is to measure the bending of the Hubble curve, one must measure great cosmic distance. So one need a gauge of distance that works to over 5 billion light years. Okay. Clearly, some very bright light sources are needed. Since this also means that we must measure objects of an age that is a significant fraction of the age of the universe, the method must also be applicable to objects present in the early universe. It turns out a certain class of supernova is ideally suited for this purpose. The type of 1A supernova begins white dwarf, which are collapsed old stars sustained by the electron degeneracy pressure, with mass comparable to solar mass. So a white dwarf often has a companion star. The dwarf's powerful gravitational attraction draws matter from its companion, so its mass increases. When it passes the Chandrasekhar limit, 1.4 solar mass, when it no longer can be countered by the electron degeneracy pressure, the gravitational contraction proceeds and result heating the core, which will trigger a thermonuclear blast, resulting in a supernova explosion. So because these supernova start with a mass in a narrow range, or around 1.4 Chandrasekhar, such supernova have comparable intrinsic brightness. Furthermore, their brightness has a characteristic decline from its maximum, so we call light curve, from which we can use to improve the calibration of the luminosity. So this will make the supernova 1A ideal as a standard candles, because we know its intrinsic brightness with some confidence. Then by looking compare the observed flux, then we know how far they must be.